Let's delve even deeper into the engineering marvel that is the human body and draw richer parallels between specific body parts and their engineering counterparts. Engineering excellence in the human body. At its core, homeostasis is a dynamic equilibrium. This balance, maintained by a series of control mechanisms, similar to control systems in engineering, ensures internal conditions remain stable. For example, our body's temperature, pH, and glucose levels are consistently regulated. In engineering, a close analogy might be a thermostat-controlled HVAC system, maintaining room temperature by adjusting heating or cooling based on feedback. Aircraft wings flex under turbulent conditions. Similarly, our bodies adapt to various environmental stressors. Muscle hypertrophy due to resistance training or erythrocyte production at high altitudes showcases our body's ability to adapt and thrive. The human gait, the cycle of walking or running, is a masterpiece of energy conservation. Similarly, in engineering, we design machines, like cars or bicycles, aiming for the most efficient use of energy. Imagine a building that repairs its cracks or a machine that fixes its wear and tear. That's our body for you. From skin cells to liver tissues, the body can regenerate and repair, a feature engineering still aspires to embed in materials and structures. Thank you. Our body's myriad systems, neurological, cardiovascular, musculoskeletal, work in synchronization. In engineering, this integration mirrors a well-tuned orchestra or a synchronized factory assembly line, where different components must operate in harmony. Let's delve into the intriguing analogies between body parts and engineering systems, exploring how nature's designs have inspired and mirrored some of our most advanced technological creations. As we proceed, I encourage you to view the human body not just as a biological wonder but as an exquisite example of engineering at its finest. So, let's get started. The brain's neural networks, consisting of billions of interconnected neurons, process information and command body functions. Modern supercomputers, particularly those designed for deep learning, emulate the neural architecture, although they're still far from the brain's complexity and efficiency. In engineering, a pump's efficiency and durability are paramount. The heart achieves both, adjusting its output, cardiac output, based on body demands, reminiscent of variable speed pumps in industrial systems. The alveoli in our lungs, tiny sacs, maximize surface area for optimal gas exchange, much like the design principle in industrial gas exchangers or heat exchangers. Bones bear loads, provide leverage, and support the body. Their microstructure, with spongy and compact bone regions, balances strength with weight. This principle mirrors composite materials in engineering, which combine materials for optimized properties. Muscles produce mechanical work from chemical energy. Piezoelectric actuators, converting electrical energy to mechanical movement, somewhat mirror this, though muscles provide a broader range of motion and adaptability. Modern communication networks, like the Internet, rely on rapid data transmission. Neurons achieve this through electrochemical signals, enabling reactions like jerking a hand away from a hot object. Just as spacecraft have heat shields to protect against atmospheric re-entry heat, our skin defends against environmental hazards, regulates temperature, and prevents dehydration. The eye's retina, with rod and cone cells, captures light and processes it, providing high dynamic range capabilities, focus adjustment, and more. Camera sensors try to emulate this with technologies like adaptive exposure. Dialysis machines, which aid patients with kidney failure, are a testament to the kidney's complex filtration and reabsorption system, maintaining electrolyte balance and removing waste. The liver conducts hundreds of chemical reactions, from detoxification to protein synthesis. It's akin to a multi-process chemical plant, processing raw materials into a myriad of products. Food undergoes mechanical and chemical breakdown, moving through different stations: mouth, stomach, intestines. This mirrors industrial processing lines, where raw materials transform sequentially into finished products. Sound waves get transformed into mechanical vibrations in the eardrum, then into fluid waves in the cochlea, and finally into electrical signals for the brain. This intricate conversion process mirrors the workings of microphones and subsequent sound processors. The human body, when observed through the lens of engineering, exemplifies sophistication, integration, and adaptability. Its components, both in isolation and together, serve as inspiration for countless innovations in engineering and technology. By understanding and mimicking these natural systems, we can aspire to create human-made systems that are more efficient, robust, and sustainable.